In this next set of examples, we'll notice that these are type 2 improper integrals. So we said that type 2 improper integrals, that's going to be when the integrand approaches plus or minus infinity on the interval of integration. So in other words, this is when the integrand has a vertical asymptote between the limits of integration. So we have to be really careful. These are harder to spot. And so this very first example, I know that the graph of 1 over x minus 1 has a vertical asymptote when x equals 1. That would make our denominator 0. And since 1 is the limit of our integral here, that's going to actually make this a little bit easier than when 1 is in the middle of, like when our vertical asymptote is between our two limits. So let's consider the graph of 1 over x minus 1, just to be able to understand what's going on here. So in Algebra 2, I learned that this is just like the graph of 1 over x, except that it has been shifted or translated to the right 1 unit. So it's going to look something like this. And we said that this vertical asymptote is at x equals 1. So now when we're trying to sketch the area between this curve and the axis, this area is unbounded, but it's not unbounded because we're cutting this off at 4, right? We're going to integrate from 1 to 4. So the area is not unbounded because of the x values or in the x direction. It's unbounded in the y direction here because we have that asymptote at 1. So this is really similar to what we did before with the other examples. We just have to think really hard about these. So if I go to sketch this, I'm going to think about where my asymptote is. So again, we said the asymptote is at 1. And just like before, I'm going to pick a value to just call it A. And I'm going to make it really close to my asymptote. And we're going to find this area from A to 4, but then we're going to allow A to approach 1. And this direction is going to be important here because A is going to be approaching 1 from the left. So we are going to integrate from A to 4, the function 1 over x minus 1, but we're going to limit this so that A approaches 1. And we know when we're working with vertical asymptotes, we've got to be really careful what side of the asymptote we're on. Since we are coming, actually before, I think I said from the left. I meant to say from the right. We're coming from the right. We're headed towards the left when we approach 1, but we need to approach 1 from the right-hand side of 1. So sorry if that was confusing the way I said that. All right, so when we go ahead and find our antiderivative, I know I've got to keep my limit statement here. So the limit as A approaches 1 from the right. Well, this is a pretty easy antiderivative. We could do a u sub here, but if u is x minus 1, du is just dx. So we could really just hold our thinking of that in our head, that our antiderivative is the natural log of the absolute value of u, which is just x minus 1 du. And we're going to again, evaluate that from A to 4. All right, I put my equal sign inside. So same as before, I'm going to go ahead and plug in my limits. So my limits of integration. So I'm going to get, when I plug in the 4, I'm going to get the natural log of 4, the absolute value of 4 minus 1, which I just know that is ln of 3. And then when I plug in my A, I'm going to get the natural log of the absolute value of A minus 1. And remember, A is slightly to the right of 1. So the absolute value of A minus 1 I really could just drop that absolute value symbol there because that's going to be positive. All right, so now we said we need to let A approach 1 from the right. And so I know that the natural log of 3 is just the natural log of 3. But as a approaches 1 from the right, a minus 1, a is just going to be a tiny, 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 tiny bit greater than 1. So a minus 1 is just going to be a tiny, 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 tiny bit greater than 0. So if I think about my graph of y equals ln of x, I know that the natural log of x has a vertical asymptote at x equals 0. And so if I'm just slightly more than 0, this whole thing here, the natural log of a number that is slightly more than 0, is going to be going to negative infinity. Like those y values are going to negative infinity. So I get ln of 3 minus negative infinity, which is the same as ln of 3 plus infinity, which is just positive infinity. So all of that work to find out that this diverges. All right, in our second example, again, we've got to be really careful here. It would be easy to miss that we have vertical asymptotes between 1 and 5, or rather a vertical asymptote between 1 and 5. So again, if I just check, if I set my denominator equal to 0, I get x minus 2, x plus 2 equals 0. So I have vertical asymptotes at negative and positive 2. So let's sketch this graph. And we could think about it, and we could spend a lot of time like reasoning about this graph. But I'm going to be honest with you, I graphed it in Desmos. I know where my vertical asymptotes are, but I wanted to just see what it looked like. So, all right, so when we graph this function x over x squared minus 4, it's going to look kind of like this. If you want to check it in Desmos, you can. We don't need the graph to be able to answer this question. All right, and then on this side, it's like down like that. Okay, so really, if I'm integrating from 1 to 5, like if those are my limits, I'm not worried about my vertical asymptote at negative 2, since negative 2 is not between 1 and 5. What I'm worried about is the vertical asymptote that is like right in the middle between 1 and 5. So I know that when I'm integrating, I'm trying to get this area here, and I see that that's unbounded, and I'm trying to add to that this other unbounded area here. But we've got to worry about this asymptote at x equals 2. So the bad news is that we really have to break this up into the sum of two integrals, because we have to split our we have to break this up where x equals 2. The good news is it won't be that hard once we do it. So we're going to integrate. So I'm going to, again, picking a value, let's say a. I'm going to say that a is right here, and that a is really, really close to 2, but a is on the left-hand side of 2. And then I'm going to pick a value b on the right-hand side of 2. So for the first part, we're going to have to integrate from 1 to a. And again, we said we're going to limit that so that a approaches 2. And notice we're on the we're coming from the left-hand side of the asymptote. So we're headed towards 2 from the left there. So I need to show that in my limit. And then I'm going to add to that the definite integral from our b value to 5. But I know this time b also needs to approach 2. And b is approaching 2 from the right. So I got to make sure I have that notation there. That limit notation is really important. All right, so when we go to integrate, again, if I realize this isn't just like any of my formulas that I know, and this is not arctan because of that x on top, What I could think about is, could I just try a u sub? So let's let u equal x squared minus 4. Therefore, du is 2x dx. And so I know that even if I just hold my thinking about this in my head, I need a 2x dx, so I need a 1/2 out front. And that's going to be the same for both of these integrals. All right, so when I go to do this, remember, if I have a constant multiplier in my limit, I can actually pull that out front. So I could pull the 1/2 out in front of the limit. Sometimes that just makes it a little simpler. So 1/2 the limit as a approaches 2 on the left. And now when I find my antiderivative, we said it's really in the form of 1 over u du, right? So we know we're going to get the natural log of the absolute value of x squared minus 4. And we're going to evaluate that from 1 to a. And then we're going to add to that. When we get to our second integral, I'm going to pull that 1/2 out in front again. So 1/2 the limit as b approaches 2 from the right-hand side. Oops, I don't know why I'm rewriting that. Sorry, we already have our antiderivative. I'm just looking at the line above. The natural log of the absolute value of x squared minus 4. And this time, we're evaluating that from b to 5. All right, so when we go ahead and plug this in, I have 1/2 the limit as a approaches 2 from the left. When I apply the fundamental theorem, I am substituting my a and my 1 into my antiderivative. So I get a squared minus 4. So the natural log of the absolute value of a squared minus 4 minus the natural log of the absolute value. When I plug a 1 in there, 1 squared minus 4 is a -3. All right, then we're adding to that 1/2 the limit as b approaches 2 from the right. Same thing when I plug in my 5. Let's see, 5 squared minus 4 is 21. So I get the natural log of 21. Since that's positive, I can drop that absolute value. And then I'm going to subtract from that the natural log of the absolute value of b squared minus 4. All right, so as we kind of think this through piece by piece, as a approaches 2 from the left, so a is going to be a number just a little bit less than 2, right? So like 1.99999, etc. So when we square that, a squared is going to be a number that's a little bit less than 4. And we're going to be so close. We're going to be so close to being at the 4 there that I'm basically going to get a 0. So I basically have 1/2 times the natural log of 0 there. And you know what? I'm not going to write the natural log of 0 because we know that's not in our domain. But what I am going to show is that this is going to be headed towards -infinity. And again, the way I know that is I know my natural log graph. So if I think about if I'm approaching 0, my natural log graph, as x approaches 0, my natural log graph is approaching -infinity. So I'm going to get a -infinity there. So we can actually kind of already tell that this diverges, but let's go ahead and write the rest of this out. So -infinity minus the natural log of 3. So that's really just -infinity. And what we're noticing here, that's telling us that this area diverges. So this area is our 1/2 -infinity minus ln of 3. All right, for the second piece, again, I've got the natural log of 21. And then as I apply my limit as we approach 2 from the right-hand side of 2. So when I square that, I'm going to get a number that's just a teensy tiny bit more than 4. But when I subtract that from, or subtract 4 from that, I'm going to basically get 0 again. And again, the natural log of 0 is as close as we could get to being negative infinity there. So we get a negative infinity for our leftmost area, and we get a positive infinity for our rightmost area. But those don't like cancel out or anything. This diverges. So again, like this one, that area accumulates to be positive infinity, but that means that this whole thing diverges. All right, this very last example. We need to know where the secant of x is undefined, or if it's undefined, between 0 and pi over 2. So remember that the secant of x is the reciprocal of the cosine of x, 1 over cosine of x. So I know that secant of x is undefined anywhere that the cosine of x equals 0, and between 0 and pi over 2, that's going to happen when x equals pi over 2. So remember, if secant x is 1 over cosine, secant squared is 1 over cosine squared. All right, so we know at pi over 2, we're gonna have an issue. We're gonna have a vertical asymptote. So if we remember our graph of y equals the secant of x, we said it's going to have vertical asymptotes at pi over 2 and negative pi over 2. And it's going to look like this. All right, so if we so if we're integrating this from 0 to pi over 2, again, we're trying to find this area here, but there's a vertical asymptote. So again, we are unbounded. So I'm going to choose a constant. I'm going to call it a, and a is going to be really close to pi over 2. So I know that when I integrate this, I need to think of this from 0. Oops, I need to leave some space. From 0 to a, I'm going to integrate secant squared x dx. And again, we're going to limit this so that a approaches pi over 2. And we are approaching pi over 2 from the left. Now, fortunately, that's a pretty easy antiderivative. So I've got my limit. And the antiderivative of secant squared x, I know, is just the tangent of x. So when I go ahead and apply the second part of my FTC, I've got the limit as a approaches pi over 2 from the left of the tangent of a minus the tangent of 0. To understand the tangent of a here as a approaches pi over 2 from the left, we need to think about the graph. I'm just going to think about the graph of y equals the tangent of x. And I remember that, again, tangent has vertical asymptotes at pi over 2 and negative pi over 2, because that is where the cosine of x is 0. So tangent's undefined. So the tangent of a, as a approaches pi over 2 from the left, that's going to be infinity. So we have infinity minus 0, because the tangent of 0 is 0. And so again, this diverges.